Every email you send, every video you stream, and every financial transaction you execute relies entirely on manipulating light as a wave. In a perfect vacuum, light is a transverse electromagnetic wave. It consists of mutually perpendicular electric and magnetic fields oscillating outward through space. But in free space, electromagnetic waves are completely unconfined. They radiate outward in all directions, and their signal intensity rapidly dissipates. To transmit high-density data across oceanic distances, we have to physically confine that energy. The engineering solution is to trap those light waves inside microscopic threads of highly purified silica glass. The ability to do this traces directly back to the electromagnetic theory established in the 19th century by James Clerk Maxwell. Designing and operating the physical layer of the global internet is strictly an exercise in applied Maxwellian physics and wave mechanics. To understand how we control light, we start with the mathematical model of a transverse electromagnetic wave. The electric field at any point in space and time is represented by E0 times the cosine of omega t minus beta z plus phi. The amplitude, E0, determines the maximum displacement of the wave. In optical communication, this corresponds directly to the physical optical power, or the received signal strength at the destination. The phase variable, phi, tracks the exact position of the wave within its cycle at any given fraction of a second. This becomes crucial when multiple waves interact. Beyond its physical shape, the utility of a light wave depends entirely on its speed and frequency characteristics. The core relationship governing propagation states that a wave's velocity equals its frequency multiplied by its wavelength. For long-distance optical communication, engineers strictly utilize wavelengths in the infrared spectrum, primarily zeroing in on the 1550 nanometer window, where glass is most transparent. If we calculate the frequency for a 1550 nanometer wave traveling at the speed of light, it calculates out to roughly 193.5 terahertz. This massive oscillation rate provides the immense bandwidth capacity of modern networks. However, that 300 million meter per second velocity only applies in a perfect vacuum. When light enters a denser material, it slows down. This deceleration is quantified by the medium's refractive index, denoted by the letter n. The actual velocity of the wave inside the glass is the speed of light divided by n. By artificially layering materials with different refractive indices, we gain the ability to manipulate the wave's velocity, giving us the precise mechanism needed to trap it. An optical fiber is built around two distinct layers of glass, a central core and an outer cladding. The entire system hinges on a very specific material difference. The core is doped to possess a slightly higher refractive index than the surrounding cladding. When light travels through the core and strikes the cladding boundary at a shallow angle, the refractive index differential forces the wave to bend so sharply that it reflects inward. This is total internal reflection. The wave is physically barred from escaping. Trapping a single wave allows us to guide energy, but to transmit data, we have to force multiple coherent waves to interact. This relies on the principle of superposition. When two light waves overlap in space, their resulting electric field is the exact vector sum of the individual waves. If two waves are perfectly in phase, their peaks align. They combine through constructive interference to create a single wave with double the amplitude. If those waves are shifted 180 degrees out of phase, a peak meets a trough. This causes destructive interference, canceling the wave out entirely and dropping the signal intensity to near zero. In optical networks, interference is not a passive natural event we observe. It is a strictly controlled variable. Hardware components like the Mach-Sender modulator exploit this exact principle. The modulator splits a continuous light wave, delays one path to alter its phase, and recombines them. By rapidly alternating between constructive and destructive interference, it carves the continuous beam into the discrete binary pulses of data that computers read. Through total internal reflection, we contain the wave. Through superposition, we encode information onto its phase and amplitude. The mathematics of a perfect wave are pristine, but pushing light through physical glass for hundreds of kilometers introduces severe distortion. Any interaction with microbends or impurities in the fiber causes diffraction, which spreads the beam and degrades coupling efficiency. The ultimate limitation of optical transmission requires us to look at a single, perfect optical pulse carrying one bit of data down the fiber core. The primary threat to this pulse over long distances is dispersion. Because the refractive index of silica glass is not perfectly constant, it varies slightly depending on the exact wavelength of the light passing through it. Real-world industrial lasers do not emit a single perfect wavelength. They output a narrow, clustered band of multiple wavelengths. Because each specific wavelength experiences a slightly different refractive index, they travel at marginally different velocities within that same optical pulse. As the slower wavelengths fall behind the faster ones, the entire pulse broadens. If left unmitigated, a pulse will widen until it completely bleeds into the adjacent bit of data. This overlapping destroys the signal. It defines the absolute physical limits on both the maximum transmission distance and the maximum data rate an optical link can sustain. To increase bandwidth, optical engineers must design waveguide structures that actively fight these natural dispersive tendencies. Mitigating dispersion dictates the physical architecture of the fiber itself. We must choose between multimode and single-mode configurations. A multimode fiber uses a wide central core, around 50 micrometers. This allows light to bounce at steep angles, creating multiple paths. Arriving at the receiver at different times causes severe modal dispersion. To solve this, engineers manufacture single-mode fiber with a microscopic 9 micrometer core. This extreme spatial confinement forces the light to propagate in exactly one path down the absolute center of the core. By allowing only one mode, modal dispersion is mathematically eliminated. Because it preserves pulse integrity, single-mode architecture is utilized exclusively for high-bandwidth, long-distance interconnects. When this ultra-narrow geometry is combined with lasers operating in the optimal 1550 nanometer window, we achieve maximum wave confinement with the lowest possible glass attenuation. Every piece of global digital infrastructure, from massive data center interconnects to high-frequency financial trading, is physically carried by these perfectly guided infrared waves. The global data network relies entirely on our ability to precisely apply the laws of pure electromagnetic wave theory to a physical thread of glass.